Okay, I heard that we're good to go. So good morning, everyone. My name is Kevin Wolf, and I assume you're here because you want to hear something about out of process storage backends. And I hope I can tell you something useful about that. So first, let me give you some background. I was already talking about out of process backends 2 years ago, and I was more going into the motivations of why you would even want to do something like that. So I'll just do a short recap of that, and then I'll go more into the details of the options that we actually have. So one reason why you would want to move the storage backends out of QEMU into a separate process might be that it just gives you better isolation, more security. You also have separation of concerns, like running VM is a different task than accessing storage, really. You might want to do log jobs, like merging snapshots, even while the VM is down. You might want to share a backing chain between multiple VMs and still delete snapshots in the shared part, for example. That's something that you can do when you have a single shared out-of-process storage backend. You might want to share CPU for polling, so for performance, it can be beneficial in some cases. Or you can share a single physical disk between multiple VMs using user space block drivers like the NVMe driver that we have in QEMU currently. So all of these are motivations why you would want to use an out-of-process backend. Of course, I'm here because I have a specific motivation to do this. Yours might be different. The talk still applies if you have a different motivation. I'll explain the characteristics of the different methods we have to achieve this. Your conclusion might be different than mine. So my specific motivation is that in the context of KubeVirt, storage is kind of considered someone else's problem. Storage is just something that's provided by Kubernetes, and then you run a VM on it. And the basic idea for that is the storage vendor just provides some software, a CSI plugin, that provides all of these operations on the storage. And in practice, we see that either the CSI driver doesn't even exist for the storage, or it does, and it doesn't quite meet the requirements. For example, it's often the case that when you request a new volume on the storage, it gives you a whole new LAN, and that just doesn't scale well if you have thousands of LANs in a Linux kernel. So from the past, we know QEMU can already do all of this. So what we want is to expose that and be able to use it in the context of Kubernetes. So that's the context in which my team is looking at this. So what are our options to achieve this? The obvious one that everyone knows is NBD. We have been using this for a long time. It's been the first export in QEMU. We're using this mainly for migration. And that's exactly where its strength is because it's a network protocol. You can use it over the network. But you can obviously also use it locally. So you can export NBD using a Unix domain socket and then just connect the QEMU process to it. Its advantage is also it has existed for a long time, so we know it works. And if you want to, you can even attach it as a host block device. As you can see here on the diagram, it's a relatively long I/O path, like both QEMU and QSD are involved in that. I'm using QSD for the external out-of-process backend. Could be any storage daemon, really. So you could plug in something else. I'm also showing both ways, either QEMU exporting the Unix domain socket, and you're connecting QSD directly to it, or you're going through an NBD block device on the host. And one of the problems with MBD is, as you can see, performance is not quite the same as if you do it in process in QEMU. Which is, as I said, it's a long I/O path, and also you do a lot of copies. The data that you're writing or reading is copied into the socket, is copied to the QSD process. So it's not really the solution that we want, and you probably already guessed so. Another problem in our context specifically is that if you have a socket is not a file, it's not a block device, but Kubernetes really expects storage providers to provide file systems or block devices. So it doesn't really match that. Except if you attach it to the host as a block device, you can do that. The problem is, I wanted to show you the numbers for this, but the benchmark didn't even complete. Like, the connection aborted. The kernel block driver was never really happy with the MBD connection. So, well, maybe not what you want to use either. Then we have a fuse export type, and we haven't talked about that much. I believe it doesn't get a lot of attention. It reduces the copying that you have. It's still not zero copy. So it does support splicing, so it could be achieved in theory. We don't do that. You still have both QEMU and QSD in the I/O path. But the nice thing is the export shows up as a regular file, so you don't have the problem with having a socket. And it works as a regular user. So while even attaching MBD to a block device requires root permissions, this just works. How does it perform? I compared actually two different Fuse implementations. Fuse master is what we currently have in QEMU. It's not great. HANA wrote some patches to improve the performance there. And it's a bit better than NBD anyway. And then we have the option of vhost user block, which I believe is what most expect, that it's the solution to do this, to have out-of-process storage backends. And it's radically different from the other two solutions in that it completely cuts out QEMU from the I/O path. So what you do is you share memory between a guest, like the guest RAM, and give QSD, the external storage daemon, direct access to that. It also doesn't require privileges. You just have shared memory. You need a Unix domain socket again to communicate between QEMU and QSD to set everything up and to share the memory. So this one should perform the same as in process in theory. In practice, it seems it's sometimes even a bit better. I don't know exactly why that is. But also, it doesn't share the same virtual block implementation, like the processing of the virtq. So it's possible there's some difference there. Of course, that comes with different problems. So as I already said, it requires a socket. We don't have a block device or a regular file in this case. And it requires the guest RAM to be shared memory, so that this actually works, that we can get this short I/O path. And there have been discussions before if we should just enable shared memory for VMs by default. And the answer was always, no, we don't really want this because it conflicts with other features, such as kernel same-page merging, memory ballooning, and a few others. So it's not something that we really want to do if we can avoid it. It also only works optimally if you use a I/O block device, because what vhost user block is essentially using the I/O block protocol to communicate with the external daemon. You can work around it by using libblock.io. We have a libblock.io based block driver in QEMU that can access vhost user block device and then can be used as a backend for anything else, like an IDE device, or if you want floppies or SCSI or whatever. But obviously that means that you have to go through QEMU again. You lose the advantage that you have the shared memory with QSD. Also, this is quite different compared to normal block backends, because you don't really have a block backend on the QEMU level anymore. It's just some vhost PCI device that directly goes to the storage daemon and bypasses the whole storage, the whole block layer in QEMU. So for existing management tools, this is different, needs to be supported separately. And finally, we have a fourth export type, which is similar to both vhost user block and the other two in a way. It's a single export type that exports to the VDPA bus in the host kernel. And then depending on how you use it, you get something that matches more or less vhost user block. That's the diagram on the left. Or you get something that matches more the NBD or Fuse use case. That's if you use the Virtual VDPA driver that essentially exposes the exported device as a block device on the host. And what you would expect is that they behave similar to those as well. So the nice thing about this is if you have both use cases on the same machine, or on the same daemon too, you only need to support a single export type. It's both VDUs, like the QEMU storage daemon side is exactly the same for both sides. And then you can decide when you use the exported block device if you want to use it with shared memory or if you want to attach it as a block device and use it that way. With VDPA, you need privileges for both modes. So while vhost user block and Fuse work without privileges, VDPA, you need privileges to attach the export to the VDPA bus in a host kernel. And obviously, that also means that you need kernel support. And it's not necessarily there in all distros yet. So you still have to select, do I want to use the shared memory thing? And then you have to use, in this case, not a socket, but a character device, which is still not a block device or a file system that we want to expose to KubeVirt in our case. Or do you want to have a block device, but then you get the slower path? So one crazy idea, I'm not sure if that's realistic at all. What if the block device had an IO control convert me into a vhost thing? It would make the block device inactive, would only return EBC or whatever when you still want to access it. And then the VDPA device actually transferred to the vhost kernel driver, and you get back a vhost character device. If we did that, then we could just pass a block device to QEMU, and it could transparently try, can I convert this into vhost and use the more optimal storage path? Like, as I said, it's a somewhat crazy idea, maybe some food for thought. I don't know. So how does VDPA perform? This looks pretty nice when you use the vhost path with shared memory, even a bit better than vhost user. That's actually something that I haven't found an explanation for. Like when I said before that vhost user block is a bit better than in process, I can explain that by it's two different implementations of the virt queues. That's not the case here because vhost user and VDPA, they share the same code. So there's some difference somewhere else. I actually found one difference, and when I tried it out to change it in vhost user, it didn't change the result. So we could maybe look into that, where the difference really is. What's next? Oh yeah, I talked about how you can use liblock.io if you want to have the shared memory path, but still not use Virdeo block as your guest device, right? And if you use liblock.io, you get a normal QEMU block backend, as if you were using just a local image file or block device. And you can use that with any kind of guest device that you want. And the performance is not worse than if you attach it as a block device first. So if you're okay with the requirement of having a character device instead of a file or a block device, and you're okay with using shared memory, then you probably want to go the vhost VDPA path. And for anything that is not Virdeo block, you can just use liblock.io, and it will perform fine. And finally, we have another possible block backend that doesn't exist in QEMU yet, and that is uBlock. We had some talk about it. The IO path actually looks quite similar to Virdeo VDPA. You have you go through QEMU. QEMU accesses a block device, so it's actually a block device. So that's nice. That's what we want to have. And then you have the QEMU storage daemon, which accesses the corresponding character device, sends requests there, basically commands fetch a request, and then uBlock just forwards the request, and QSD can process it. We don't have an implementation in QEMU for that yet, though it's doable. While trying to implement something, I didn't do it in QEMU for now, but I started with the Rust storage daemon. I noticed that the kernel driver is not very mature yet, so there's some work left to do there. But it's, you know, if the theory is what we want, then we can work on that and improve it. So how does this perform? This is a bit harder to tell because, as I said, it doesn't exist in QEMU yet. So what I had to do is use the UBD server, which belongs to the uBlock project. And it does things a bit differently because all of the things that I benchmarked so far in QEMU, they used a single thread. Now, UBD serve uses one thread per queue, and I tested with 4 CPUs, so get 4 queues and 4 threads. So these are not completely comparable. To make it comparable to in-process, at least, I ran the in-process benchmark once again with 4 IO threads assigned to the single device using the multi-queue code that we merged only recently. And that's what you see on the left now. So performance is not bad, but it's also not in the level that you get with shared memory like in vhost user or vhost VDPA. So what's the conclusion from all of this? I really want to take some properties from each of the things. Like everything that we want exists somewhere, just the combination of everything doesn't really exist. In particular for performance, it seems important that you have zero copy and also that you don't have too many context switches like the shorter IO path it shows too. But the problem is that sharing memory and giving access to the memory from the storage daemon is kind of painful and it costs features. Yeah, you can't use other features. Anyway, if the privileges are not a problem, and if you don't have a problem with shared memory, then VDPA seems to be a good export type that performs well in both ways, like vhost VDPA and the Virdeo one that exposes a block device. But obviously, you still need to do that trade-off when you choose how to attach it to the host. Now, obviously, the question is, can we improve anything here in the situation? And if yes, which export type do we want to improve. So for us, it seems that we almost certainly want a normal block device or file, which already limits us to the export types that currently don't perform as well as we would like them to. But the limitations of shared memory just seem hard to overcome. I don't see how we can improve there, though it was mentioned to me that some people are working on it. Maybe we will get an option there. And bypassing QEMU's block layer also makes the management very different, so it's more difficult for management software to work with this. So we really want to have a block device or a file. And in that case, we don't really have a way to remove QEMU from the I/O path, except I had the thought, there was talk a while ago about doing an I/O urine pass-through, and in that way, the guest could directly access the block device. I'm not sure if that's something that's still under consideration or not. That would maybe be the only way out there. But what you can do is try to reduce the overhead on the QSD side. Like so far, we have always tried to remove QEMU from the path. Maybe we can do something on the side of the external daemon. So one optimization for uBlock that is currently on the mailing lists is something that actually provides zero copy. Because often the user space daemon doesn't actually do anything with the payload that you're copying into its memory. The only thing it does is it takes it as a buffer to write to an image file or to read from an image file. So there's no real reason to even copy it into user space. If you could just access it with the next command that the storage daemon is issuing to the backing image. And if it's using I/O urine, then with uBlock that can be done in that way that you couple two requests. The first request to I/O urine is give me the buffer that is related to this request I just got from you, and then do a read or do a write using that buffer, and it never goes to user space. So this one is in review upstream. I expect that sooner or later this will probably be merged. The next thing that we could do, and that I wrote a prototype a while ago for, is what if you skip user space completely? Like in many cases, the user space doesn't do very complicated things. It just maps things to a different file descriptor and a different offset. And we can just cache that in the kernel and then not call into user space at all. So in this case, we're not cutting out QEMU from the I/O path, but we could cut out QSD from at least the hot path. And only if you need to do, I don't know, allocate new blocks or something like that, you still go to user space. And then another idea that came from that, from Ming Lei, is, well, if we're moving things into the kernel, why not have code in the kernel? Like you upload ePPF code to the kernel for handling requests. Then you can only do mappings, but you could also do things like updating a dirty bitmap, stuff like the QEMU block layer usually does. You could just do that in the kernel as well. There is some early prototype code for that. I don't know what comes out of that, or if it's a good idea even. And finally, I have made a few other optimizations, observations, what you could optimize in other block drivers. So the first thing is the difference that I noticed between vhost user block and VDP-I/O block. They have different queue size by default. That seems to be an accident because it was updated at one point for all of the VirtIO block implementations except vhost user. So we probably should just fix that. But as I also said, it didn't really fix the performance difference. I also mentioned that uBlock, the default server, uses multiple I/O threads. We should probably implement that for exports as well. Like we did for the VirtIO block device itself, export should do the same. And finally, something seems to be wrong with the MBD implementation. It performs slower than I would expect from the thing that it's doing, like from the architecture. So finally, I only have some bonus data. That's mostly for when you view the slides after the talk. These are all of the results together. First, for a null device, which shows purely the overhead of the transport. So I think that's maybe one of the more interesting ones. And as you go to slower storage, to disks, you see that most exports perform roughly the same because the disk just slows things down. And finally, I did the same on an encrypted file system, my home directory on a laptop. And you see, MBD is the one that really doesn't perform well there. There's something else going on, like it's not handling parallel requests right or something like that. And that's all I have. So if there are any questions.
I hope I remember everything that I have to ask. Can you go to slide, I think, 23?
23?
Yes.
This one?
Yes. When you say bypassing QEMU's block layer, do you mean QEMU, or does QSD also count as a QEMU block layer?
No, in this thing, I mean bypassing QEMU's block.
Okay, so it's like it also makes it different if you can write QMP commands to storage daemon, it's still pretty different.
Well, I mean, even the fact that you need to send things to the storage daemon is quite different from what you used to do. So
yeah. So second question is, when you use libblock.io to convert the host to a random device, can it do like stuff like map the guest memory and pass the mappings to the host user so that you can do the DMA into?
Yes. So it still uses shared memory.
Yeah. Yeah, exactly. Yeah.
I think that how efficient that is, it depends on whether the guest device actually supports that. Like, I believe vhost block has some specific code to enable that, right, Stefan?
So I think the idea is roughly similar to the NVMe backend, like where in that case you have to pass it to VFIO. In this case, you pass it to the host user, the memory map of the guest.
Yeah, so basically, I think you have to register the RAM with the backend, and when that is done, it just uses the shared memory.
And third, and sorry everybody, but final question. For the privilege issue, have you looked into using Satan?
No, I haven't.
Okay.
Maybe I should.
Thanks. So one comment is you said, I'm not sure why VDPA was so fast in some cases.
Compared to vhost user, yeah.
I don't know if it's still the case, but VDPA pinned memory in the past.
Okay.
So I wonder if all the guest RAM was all pinned, and maybe that affected the performance.
Interesting thought.
Yeah, should be the case. The only way when we don't pin the RAM is when we use you need a special flag to and so every time the address is mapped and unmapped. But yeah, the default case, it will pin the entire RAM.
Maybe we can test that.
Yeah. Yep. And I mean, just a question. Similar to, you mentioned that uBlock, with uBlock we can change it and make essentially make the uBlock device access directly the storage in one slide. Maybe we can do something similar also with VDPA, implementing the VDPA device into the kernel.
Yes, I think then you're essentially back to vhost block, like the in-kernel thing.
Right. And then you don't have the copy anymore in using Virta.io VDPA.
Right. I mean, it's a bit more challenging, I guess, than uBlock, because uBlock automatically sees this thing as a storage device, and in this case, you have to implement a Virta.io block, implementation in kernel. And it seems we're out of time.
Oh, so then okay.
So just catch me outside later.